Hey, welcome! Today, we're jumping into a topic that, honestly, is make or break for anyone in the medical device world. We're talking about making sure your product actually survives the trip from your facility to the hospital or clinic. It's all about mastering transport validation.
So let's just start with a really big question. Think about it. You've poured so much time, money, and brainpower into creating this incredible life-saving device. But how safe is its journey? You see, the second it leaves your door, it's basically on this wild, perilous adventure, and its survival is absolutely not guaranteed. Okay, so let's get right into it. Why do we even have to do this? Why prove our packaging can take a beating? Well, the short answer is because you have to. It's the law. This isn't just a nice to have or a best practice. It's a non-negotiable requirement under the European Medical Device Regulation, also known as the MDR.
Right, so this whole legal framework is built on a few key pillars. You've got the MDR at the very top, that's the rulebook. It tells you what you need to do. Then you have these incredible standards like ISO 11607 for sterile devices and the star of our show today, ASTM D4169. These are the how-to guides. They give you the specific scientific methods to prove you're actually following the rules laid out in the MDR. And this right here, this is the heart of the matter, straight from the regulation itself. And look at the language. Intended characteristics and performance are maintained. This means it's not just about the box showing up without a giant hole in it. It's about guaranteeing that the device inside works exactly as it's supposed to. If it's a sterile implant, that sterile barrier has to be perfect. No excuses, no exceptions. So before we can even think about testing our packaging, we have to understand the enemy, right? We need to know what we're up against. Let's talk about the real-world villains of this story, the hazards that are going to be attacking our package every step of the way. And here they are, the four main horsemen of the shipping apocalypse. You've got temperature and humidity swings. Imagine going from a frozen warehouse to a scorching hot, humid loading dock. Then there's vibration, that constant, relentless shaking from truck engines and bumpy roads. Of course, you have shock, accidental drops, bumps, things shifting around. And finally, pressure. And I mean the literal, crushing force of other heavy boxes being stacked on top of yours. Okay, so we know the dangers. Now, how in the world do we prove our package can survive all that? Well, you've basically got two paths you can take. You can try to test it out in the messy, unpredictable real world, or you can bring all that chaos into a controlled lab and simulate it. Now, sending a few boxes on a real truck ride might seem like a good idea, but it is just riddled with problems. How do you know what really happened to it? How do you document it? Plus, a trip in July is totally different from one in January. It's expensive, it takes forever, and it's a roll of the dice. That is precisely why the entire industry leans on laboratory simulation. It's repeatable, it's efficient, and best of all, you get to simulate the absolute worst-case scenario every single time. So let's talk about the hero of this story, the ASTM D4169 standard. We're going to focus on what's called Distribution Cycle 13, or DC13, which is pretty much the go-to testing sequence for medical devices. You should really think of it as the ultimate standardized obstacle course for your package. So, what is a distribution cycle? Well, simply put, it's a recipe. It's a specific sequence of tests done in a specific order that's designed to mimic the entire journey from start to finish. It simulates being handled, being stacked, being shaken on a truck, maybe flying in a plane, and then getting handled again at the very end. It's the whole trip, just, in a lab.
And here it is. This is the gauntlet. This is the list of challenges your package has to run. It starts with some drops, then gets squeezed, shaken around, put in a low-pressure chamber to simulate being in an airplane, shaken some more, and then, for the grand finale, it faces an even tougher drop test. Each step is a carefully chosen simulation of a real-world event. But wait, before any of the physical abuse can begin, we have to prep the package. It's called environmental conditioning. Basically, your package gets to hang out in a climate chamber for up to 3 days to experience different temperatures and humidity levels. We're getting it ready for the journey by simulating everything from a frozen Swedish winter to a humid Singapore summer. And these are some really common conditions that regulators like the FDA often want to see. We're testing to see if the packaging materials get brittle in the freezing cold or if the glue fails in extreme heat and humidity. We have to make sure the box is up for the challenge before we start dropping and shaking it. All right, okay, the simulation is finally over. The box has been through the ringer. It's been dropped, crushed, and shaken. it's probably looking pretty battered and bruised. So, what now? How do we actually figure out if we passed? Was the mission a success?
The final analysis is really a two-part investigation. First, you look at the package itself. For sterile products, that means running integrity tests, like a dye leak test, to make absolutely sure the sterile barrier is still intact. But then, and this is the most important part, you have to test the device that was inside. Does it still work perfectly? Does it meet every single one of its performance specs? Both the package and the product have to pass.
And this, of course, leads us to the million-dollar question, the one everybody wants to know. Okay, so how many boxes do I actually have to send to the lab to put through this whole ordeal for my validation to count? And I'm going to give you the most honest, if slightly unsatisfying answer. It depends. I know, but there's no magic number. The right quantity comes from a risk analysis of your specific product. Are you shipping a huge, complex machine or a tiny, delicate sterile implant? Do you have one box size or 20? The number of samples has to be statistically significant, so you can be confident that your packaging system will work every single time.
And that really brings us to the finish line. Transport validation isn't just about ticking a box for the regulators. It is the ultimate insurance policy for your product. It's what ensures that all the incredible work you did designing and building that device isn't completely undone by a bumpy road or a clumsy moment. So, I'll leave you with this question to think about. Is your packaging truly ready for the journey ahead? Thanks so much for tuning in.